Any questions before we go on?
Last question from your last lecture. Day2 path.
Yes.
I tried to solve it, but cannot solve the equations.
This one. Well, for this one, you don't even need equations to solve it. Okay, anybody who wants to explain why it is the path 1 that takes the shortest time? If you want to explain though, just saying that, okay, it moves faster in the lower path doesn't really answer it. Because on one hand, it goes faster. On the other hand, it has to cover a larger distance. So you have to make sure that whatever the difference in the distance is, it will always, the particle that goes through the first path will always take a shorter time, independent of the change in the length of the distance that it has to cover. No, never. It will be always ignoring friction. There is no friction, there is no dissipation. So you just release your masses at the same point at the point A, and the one that takes the path 1 will always reach the point B at a shorter time. Well, the time difference will of course depend on the actual path, and in fact probably the longer this path is, the shorter it will take. But it will be always this one that goes first.
No, I can try to explain. Firstly, we are only interested in horizontal velocity.
Why?
Because their initial and final points are same. And I take them as horizontal. How can I say? For path 2, there's a horizontal way. And for path 1, they're also vertical way, but we are interested in final points, and they are in a horizontal plane. So that's why I'm taking only horizontal.
Well, we had already seen in kinematics that all the x, y, and z components of the motion, they are independent of each other. So a three-dimensional motion or a two-dimensional motion is nothing but a collection of one-dimensional motion in each one of the directions. So that's why your friend is taking only the horizontal component.
We all can say the entrance to path velocity is the same in magnitude. They are physically the same. But for first path, it will accelerate downward. It will accelerate because of gravity, and its velocity when it comes to horizontal path will be greater than its first speed. The first speed, and for path 2 objects, it will always stay the same. It will always the same. But the object on the path 1 is nevertheless have even slightly greater, depending on the path, slightly greater horizontal speed. Its velocity on horizontal plane will be even definitely more than the second path speed on horizontal. On X, it will always have speed definitely more than for second path. Since the horizontal path length are the same, it will definitely go first.
Now you see, if you just, are you convinced that it's enough to study the horizontal component only? You are not convinced? True. True. That's the critical thing is, one is to separate the motion. The horizontal motion and the vertical motion, they are independent of each other. You can just study each one of these motion independently. And once you determine that it's enough to study the horizontal motion, you see in the first path, as your friend pointed out, you can either go straight to this horizontal part. In the horizontal part, you are all convinced that it will have a larger speed. Well, the only velocity component it has is the horizontal one, so this one will have a larger horizontal velocity. So it will cover the same distance at a shorter time. Or you can say that, okay, at this point, this is the normal force acting on my object, which will be causing my object to have a horizontal acceleration. So the horizontal speed will increase, and here, this is the direction of the normal force, so the horizontal speed will decrease. So both of the objects will reach this point with the same horizontal speed. The one that takes the first path will have a larger horizontal speed. It will first accelerate in this region and then move with constant horizontal speed. The second one will just go straight. So this is the first one, this is the particle that takes the second path. Now in the case of the third path, so this is the normal force. So its horizontal component of this normal force will cause this horizontal speed to decrease. So this is the third path. So what we want is all of the particles should cover the same distance. And we also know that the distance is nothing but the area below the VT diagram. So the first particle, this one, should reach the end point first. Then the horizontal speed will be, Of course, the horizontal speed will not be constant, it will increase as it's rolling down. And then the first particle the horizontal speed will increase, then in this region it will decrease, and then it will be constant. And this is when it reaches the point B. Whereas the second particle, it should come until this point. Okay, so it moves, it is still within this region, these 2 points. Only at this point, it will reach the point B. Now the area below this black line and this red line, they are equal, so that the black line should go up to this point, the red line should come up to this point. Now for the other one, it should go even further. So its speed is lower, so it will take a larger time to pass the hill. When it passes the hill, it will have the same horizontal speed as the other ones, and it should just continue until it reaches the point B. Again, the area below each one of these colored lines is just this horizontal distance, and it should be identical. So the red one reaches the point B first, and then the black one, and then the orange one, independent of the path difference. The first particle takes a longer path, but it is going much faster. So it more than makes up for the difference in the path. Because although the path that they should cover are different, the horizontal distance they should cover is the same in all of them. Any questions on this one?
Understand that's why the horizontal distance is enough for us. Because the first one is also have vertical.
Fine. But you see, if If the particles cover this horizontal distance, then they reach the point P, right? So that's why we are studying the horizontal component only. Because for the red particle, it covers that horizontal distance at this time. And we had already seen in kinematics that you can separate the components of the motion. The horizontal and the vertical motion, they're kind of independent of each other. Unless, of course, the force depends on the various components.
So we think relative, should we think relative because the increase on velocity is greater than the path?
Sure. Well, that is what it turns out to be. The reduction in time due to the increase in the velocity is more than the increase in the time due to the length difference, length increase. Okay, now I have been receiving these questions, especially after probably the first midterm, that you are studying hard, but you don't think it is enough. And how should you study? Unfortunately, I don't have an answer for everyone. I don't even have an answer. I only have an answer for myself. But I do believe that there are certain things that will affect your success. One, come to the class prepared. I'm already knowing the material. I mean, some of you, I know that you have fallen behind, so you are just trying to catch up. But, okay, that's kind of a complicated situation, because if you try to catch up, you will be missing what we are covering. So try to concentrate on the course also, while at the same time trying to catch up. Now, coming prepared, the only thing I can do is just ask you to prepare the pre-reports. That's the purpose of the pre-reports. I can only ask you to prepare the pre-reports. Now, of course, pre-reports doesn't mean that just write a couple of sentences, write a couple of questions. And if you want to really benefit from the pre-reports, you should read the chapter carefully in advance, so that you will have time to think over what we will be covering in advance. So when you come to the class, you will have already a skeleton of the material that we will cover, and you will, of course, have questions, so you can ask the questions. Now, of course, I mean, some of you are doing a good job in pre-report. Some of you are just thinking that it's just a waste of time and just preparing a couple of sentences and just a couple of relevant or irrelevant questions. Well, there's nothing much I can do about that, and I will not be trying to do anything about that, but you have to come prepared. Now, the second thing, ask questions. You should ask questions. I mean, some of you think that, okay, the things that you don't understand is so trivial that you don't want to disturb your friends, but believe me that more than half of the classroom are having the same kind of questions. The so-called, you think that you're the so-called stupid questions. And those will be the questions that will really help you to learn. Now, you are kind of an unlucky class in the sense that there's nobody in the classroom asking these stupid questions. So in the previous years, there were at least one or two students who were asking these stupid questions. So all the rest were learning from them. But in this class, there is none. So at least some of you should consider sacrificing yourself. Solve questions. Not limited to the homework. I mean, the homework is kind of, those are the questions that I can ask, and we can grade in a reasonable amount of time. That is what limits the questions. So at the end of the chapter, there are many questions. Pick some up. Ask your friend to pick up questions for you so that you will solve those questions. Or ask your friend to ask you questions. Because when you ask questions or when you pick up questions from the end of the chapter, as people, we always have the tendency to pick up the questions that we can solve. But the idea is to figure out the questions that you cannot solve. That will be the most beneficial for you. If you can figure out which kind of questions you cannot solve, then you can just concentrate on that material, learn that material, improve yourself. If you just pick up questions that you can actually solve, it won't be contributing to you. And the homeworks, as I said, is just a limit. It's not enough to solve the homeworks only. Solve more questions. And discuss. Okay, when I say that, okay, you should ask questions or you should discuss, most of the time the answer I get is, oh, I ask my friend if I don't understand something. But also you have to discuss, what did you understand? Did you understand it correctly? Are you sure that what you understand is correct? Are you sure that you can explain what you understood to your friends? Well, that is probably the most hardest part, trying to explain something to somebody that doesn't understand it. If you can do it, in that case, you can say that you have actually understood the material. So if when you explain to your friend what you have actually understood, probably they will object to you. They will say they will have understood something else. So this way you can figure out, each one of you, what did you understand correct, what did you understand wrong? And of course you can come to me, ask questions to me. Now this discussion, one thing that I'm trying to do is the forums. Now there is this forum in Hour2 class that you can use. I have heard that some of you have already formed some WhatsApp groups where you can discuss. In previous years there were some Facebook groups, that's also fine. But if you're discussing, at least in Hour2 class, I can follow, and if I need to interfere, I can interfere. But it's up to you where you want to discuss. The important thing is that you should discuss with your friends. Not just the things that you don't understand, but also the things that you understood, to make sure that you all understand it correctly. So these are the suggestions that I can give to you. Work regularly. Now, some of you were mentioning that you just study hard, but once you solve the question, it's all gone. That's probably because you are not really working regularly. I mean, if you just work for the exam, for example, that's one of the common practices. If you just work 1 week before the exam, you will probably be getting some higher grades in the exam, but 1 week after the exam, you will not be remembering anything. And everything that we will be doing is actually building on each other. So we started from mechanics, we had to describe what we mean by the force, and from the concept of the force, and now we have built the concept of the potential energy, and now we will be continuing again, starting from the force, we will be building our new concept like the momentum. So if you don't understand the concept of the force, which most of you are still having trouble understanding, you will not be able to follow what we mean by the potential energy, what we mean by the momentum. So you should still be asking your questions about the force if something are not clear about the force. Now these are the only suggestions I can give. Will they work? Most probably they will. But the problem is, will you be able to practice these? But that's kind of up to you. Now, any questions about the force? It's the 3 Newton's laws, they are the important, they are the basis of everything we will be doing in the semester. So if those 3 laws, the applications of those 3 laws are not clear, then you should ask it. No matter whether we are at the end of the semester or not, you should always ask them. For example, Newton's third law. If you state it just like that, okay, it's only action-reaction pairs find as trivial. No, it's not trivial. I mean, that's what you have seen in the midterm. There are so many of you who couldn't apply Newton's third law to this train example. Or there are so many of you who are getting confused. About this friction force, which is the reaction pair to this one. So if you think that you know an example where the action-reaction, the Newton's third law, these action-reaction laws do not hold, you should ask it. Ask in the class, ask your friends, because there is no exception to Newton's third law, at least this semester. There is no exception to Newton's second law. There is no exception to Newton's first law. If you think that there is a case where these 3 laws, or at least one of these 3 laws, do not apply, ask it. Now, any questions? Yes.
I have some stupid questions.
Great. I like stupid questions. Well, we don't know. It just seems to be how things work in nature. That's an observational law, let's say.
How can we know that it's equal in magnitude and opposite in direction?
Let's discuss momentum. That is something we can do. Because we will be discussing about the momentum conservation. It is a direct consequence of Newton's third law. If momentum is not conserved, then Newton's third law cannot be valid. If Newton's third law is not valid, then momentum cannot be conserved. So we don't directly measure, even if we say that, okay, we don't measure Newton's third law, we are measuring momentum. And we know that momentum is conserved. Now let's start with Newton's second law. Okay, this is the mathematical expression for Newton's second law, and we know that the acceleration is nothing but the change in the velocity divided by the change in time. Or I can just play with it a bit. The force times delta t is m delta v. So what this means is we exert a force on an object for a length delta t. In that case, of course, the velocity of the object will change, and this f times delta t is related with the change in the velocity of the object times the momentum, times the mass, which we can write as m times v final minus v initial, or this is mv final minus mv initial. But this is nothing but, if I put the parentheses in a different form, f times delta t is the change in this product. So you construct this quantity, it's not the velocity, you take the velocity, multiply it with the mass, and if you exert a force on the object for a duration delta t, then this product will change its value because, well, velocity is changing its value, and the change in this quantity is directly equal to the force exerted on your system times delta t. And this quantity is what we define as the momentum. This is the definition that we use. Okay, this definition is independent of the acceleration, independent of the position, independent of anything else. It only depends on the velocity of an object. If the velocity is changing, the momentum is also changing. Any questions on this one? Now let's imagine two objects. This is m1, this is m2. Let's assume that they are moving at some velocities. And furthermore, let's assume that they are exerting forces on each other by some means. And we don't need to know the specific detail of the forces, but let's just assume they exert some force. There might be a string connecting them which will be creating the force, or some other means that they will be exerting forces on each other. And these forces can be in different directions. Let's say this is the force acting on 1 due to the mass 2. And then we know Newton's third law. If Newton's third law is valid, then if this is the force exerting on mass 1 due to mass 2, there should be a similar force acting on mass 2 due to the mass 1. And Newton's third law just tells me that F12 is equal to minus F21. Now suppose that these forces, we exert these forces, these two masses exert the forces on each other for some time delta t. So F12 times delta t will be equal to minus F21 times delta t. I mean, it's multiplying both sides of this equation by delta t. But we have just seen that the force acting on an object multiplied by some duration, assuming that the force is constant within that delta t, or we can choose this delta t to be very short. so that F doesn't change within this delta T. Force acting on an object multiplied by some time is equal to the change in the momentum of the object during that time. Now, this is the force acting on mass 1. Let's assume that for the time being at least that there are no other forces acting on my masses. Only they exert forces on each other. So I have the force acting on mass 1. I'm multiplying with delta T, but that is nothing but the change in the momentum of the first mass. This is the force acting on mass 2. There's no other forces acting on that one. So the force acting on mass 2 multiplied by some time duration, that is nothing but the change in the momentum of the second mass. So as the momentum of one of the masses changes, the momentum of the other mass also changes in equal magnitudes but opposite direction. So if one gains momentum in the upward direction, the other one is gaining momentum in the downward direction. So the change in the momentum of the first mass plus the change in the momentum of the second mass is equal to 0. Delta P1 plus delta P2 is equal to 0, but this is the change in the sum of the momentum. I don't know the forces. I don't even care about the forces. What I know is if I have these two masses, if they exert some forces on each other, satisfying Newton's third law, then the change in the total momentum of my system in a very small time interval is 0. Well, a finite time interval is nothing but a collection of very small time intervals, and in each one of these very small time intervals, the momentum does not change. Exactly, it doesn't change. So in this finite interval also momentum doesn't change. But if something doesn't change during the motion of the objects, you see P1 changes, momentum of each one of the object is changing because they are exerting forces on each other. But the sum doesn't change. So this P1 plus P2 is conserved. You can just review your arguments from the last to the beginning. We derive this result assuming Newton's third law. If Newton's third law is valid, then we know that the momentum has to be conserved. If momentum is conserved, just follow these steps in reverse, and you will arrive at Newton's third law. So it's a direct consequence. Newton's third law, you can say that, okay, momentum conservation is a direct consequence of Newton's third law, or Newton's third law is a direct consequence of momentum conservation. So we know in experiments that momentum is conserved. So Newton's third law has to be valid. Newton's third law. Well, what does Newton's third law tell me? Okay, what does it mean? So apply to this case. I have these two masses. This is exerting a force on this one. Let's say this is my mass 1, this is my mass 2. So my mass 2 feels the force due to the first mass, which I call F21. And then my mass 1 feels a force due to the second mass, which I call F12. So what does Newton's third law tell me? For these forces, Newton's third law just tells me that if A is exerting a force on B, then B should be exerting a force on A, equal in magnitude, opposite in direction. So this is the expression. F12 and F21, as vectors, they are equal but pointing in opposite direction. This is what this -1 tells me. So this is the expression of Newton's third law. And once I have that Newton's third law, I have this equality, I'm just multiplying it with some length of a time interval. But this product, force times the time interval, is nothing but the change in the momentum of my object. So if the change in the momentum of these objects are related by this relation, so if I sum them up, you see, during the motion, these two objects will be doing some motion. And during that motion, due to these forces, their momentum will be constantly changing. But the change in the momentum of one of them is equal to minus the change of the momentum of the other one. So if I sum these two quantities, P1 and P2, if I look at the sum of these quantities, if this momentum is changing in this direction, the other momentum is changing in the opposite direction, the sum will not change. That's what we mean by momentum conservation.
The change of momentum we talked about force it's not important. I don't care.
We don't care about the forces.
Because momentum is force change of time.
Okay? You see, if you want to find the change in the momentum of the first object, then of course you have to study the forces. But if you are not interested in the momentum of one object, but the momentum of the general system as a whole, then the nature of the forces that they exert on each other is irrelevant. Well, this is another conservation law, just like the mechanical energy. If you just remind yourself our discussion on the mechanical energy, we had this, if you remember, for example, the roller coaster example. We were trying to find the speed of the object at the top of the roller coaster. Now, if you want to use the forces, then you can still study this problem, but you have to figure out the force at every point on the trajectory of the object. We know that at least there is a normal force which is constantly changing. Well, the weight doesn't change, the gravity doesn't change, but there is this constantly changing normal force. We have to figure out what the normal force is at every point on the trajectory. And it is doable, but it will be a lot complicated. But then we had this concept of the conserved mechanical energy. We didn't care what happened in between 2 points. The only thing we cared about was the initial mechanical energy and the final mechanical energy. If mechanical energy is conserved, that is in the absence of non-conservative forces, these two have to be equal, independent of what happens in between. This is more or less the same thing. We don't really care about the forces that they exert on each other. The thing that the Newton's third law tells me that if I have these two objects, and if they exert on each other, some forces on each other, by Newton's third law, the momentum lost by one of them should be gained by the momentum of the other one. So the sum doesn't change. That is what we know, independent of the forces. Well, in a sense, this is more general than the conservation of mechanical energy, because to discuss the conservation of mechanical energy, we have to first classify the forces. We had said, okay, we have the conservative forces, non-conservative forces, and only if we have conservative forces, and we don't have any non-conservative forces, then the mechanical energy is conserved. Here, the only assumption we make about in the conservation of momentum is that Newton's third law should be valid. If Newton's third law is valid, in that case, Newton's third law is valid all the time, in that case, momentum of your system is conserved. So this law, conservation of momentum, has a more general validity than the conservation of mechanical energy. Even if there are dissipative forces, momentum conservation holds. Questions?
So the force is defined at the rate of the change in momentum.
That's another way of looking at the force.
This is not my question.
Hmm?
This is not my question. If we define the rate of change in momentum, so how can we define momentum in terms of force? Can we say that if a force acting during some time?
Well, if you have a force acting during some time, it will change the momentum of the object. Other questions? So what was the momentum of the book? What was its direction? Okay. What is the momentum of the book now? So how can we talk about the momentum conservation, which is supposed to be valid all the time? Well, there are external forces, but what happened? Well, okay, there are external forces. That's one answer. But let's look at the whole system, the book and the Earth. There are no external forces. Ignore the sun. How? Somebody else? Somebody else? Somebody else? Come, there are already 3-4 people asking questions. No, we said that even if there are non-conservative forces, momentum is always conserved.
I think the Earth speeds increase.
The Earth?
The Earth speeds increase.
True. I mean, if you look at the closed system, you have to always look at the closed system. In this case, we ignored any external forces. There were only forces acting on my masses between them. There are no third object exerting forces on these ones. Only in that case, the force is conserved. Sorry, the momentum is conserved. Now, let's look at a couple of more things. First, let's try to generalize. Here we are only talking about two objects. Now, if you have, let's again have two objects. This is mass 1, this is mass 2, this is F1, this is F2. So they might be moving in arbitrary directions. V1, V2. Now let's look at what happens if there are external forces. So these are the net forces acting on my object. Now I can say that F1 is equal to, okay, there will be some external force. Like, for example, I can imagine these two masses. I can just throw them to each other, and then they will just hit each other. There will be some complicated forces acting on they will be exerting on each other. But there's also the weight of the objects. So there's the weight plus there will be some forces that they will exert on each other when they hit each other. It will be a complicated motion. So the force there will be too big. I can just split it into two. The external force, which might be caused by some third object, plus some internal forces. The force acting on the first one due to the second one. Plus, I can talk about the second force, the force acting on the second one. Again, there might be some external forces acting on it, plus F21. Now let's look at the change in the total momentum of my system. Well, I will be basically repeating my previous discussion, just taking into account that now there's some external force. This will be equal to change in the momentum of P1 plus change in the momentum of P2. Let's just say that we are studying our system for a very small amount of time. And I'm looking at the changes in the momentum within that very small amount of time. Well, the change in momentum of the first one is nothing but the force acting on it multiplied with the time interval, plus the change in the momentum of the other one will be F2 times the time interval that force is exerted. So this will be equal to F1 plus F2 times delta T. Now if we just sum these two forces, again keep in mind that we have Newton's third law. And Newton's third law, well, this time Newton's third law just relates these two, not the external forces. We don't know what the external forces are. But these two, they are just forces pointing in opposite directions, have the same magnitude. So if I just sum these two, it just gives me 0. What is left is only the external forces. Or in short, there's the change in the momentum. The total momentum of the object is the total external force acting on my system times delta t. Now let me denote by capital P the total momentum. So we know that the change in the total momentum of my system is the total external force times delta t. Now the internal forces, they just cancel each other because all the forces should follow Newton's third law. If all the forces are following Newton's third law, the internal forces should be action-reaction pairs. Now for these external forces, there are of course also other action-reaction pairs. So in this example, for example, this one, the Earth is pulling on this one with the weight, but this one is also, my pen is also exerting a force on Earth whose magnitude is equal to the weight of my pen. But those momentum, that force, that reaction pair, the force that my pen exerts on Earth, will be changing the momentum of Earth, and I'm not taking that in this total momentum. So that is why the external forces don't seem to be following the action-reaction pairs, mainly because the other pair is not included in this sum. The other pair is acting on something else whose momentum I'm not calculating. But the internal forces, they will be following the Newton's third law, and so they will cancel in the sum of the forces, and we are left with this one. The change in the total momentum of the system is equal to the total force, total external force acting on my system times the time it applies. Now this is for two masses. You can generalize it. The P will be nothing but the sum of the moment of each part of the system, and F, total external force, is the sum of the all external forces acting on my system. In fact, this is kind of our first step to go beyond point particles. Now, up to now, although we didn't state it explicitly, we were always assuming that the masses that we are studying are point objects. Although they were not point objects, we were assuming, we were treating them as if they were point objects. Now, this result is our first step to prove that what we were actually doing was correct. You see, if you look at this one, this is not Newton's second law. But nevertheless, I can write it as the external force is equal to dP by dt. Just compare it with F is equal to dP by dt. This is Newton's second law. It is valid for point objects. This is an extended object. Well, in the special case, we were just treating two objects, but just take any solid, any object. This is just a bunch of points. I can calculate the total momentum of this object by just summing the momentum of each one of the points making, each one of the atoms making this object. That is the total P. Then I can calculate the total external force acting on this one by just summing over the external forces acting on each one of the atoms. And then the total external force and the change in the total momentum just follow this relation, just like the Newton's second law for extended objects. Now, of course, here, some of you were asking, when we were discussing Newton's second law, we were ignoring internal forces. Well, we can ignore the internal forces in this study, in this calculation of the total external force, basically because they form action-reaction pairs, and in this sum, they just cancel. Now, I can also write this sum like this. This is also equal to sum of Fi. Because Fi, part of it will be internal force, part of it will be external. The internal parts, when I take the sum over all the particles making my system, it will just cancel. Any questions up to here?
This is valid for the formal system.
For?
Deformable system. Deformable. System that can be deformed.
This is valid for any system. For example, if you just have these two masses, well, let me take some chalk. I have one chalk. I can just say that these two chalks are my system and their shape is constantly changing. This is still valid.
But Newton's third law is not valid. But Newton's third law is not valid.
Newton's third law is actually for point objects. But now we have proven that we can use Newton's third law, second law. No, sorry, you were saying about third law? No, third law will also be valid. But you might have to interpret it somehow. You see, this external force acting on the object is due to, let's say, Earth in this chalk example. So my system as a whole, both of the chalks, will be exerting a force on Earth. And these will still be action-reaction pairs. Third law is also valid.
And second law?
It is valid in this form. First law is valid. I mean, all the Newton's law are valid all the time. It might just take different forms depending on which kinds of systems you are studying. Originally, they are valid for point objects, but now we had just seen that they are also valid for extended objects. Third law is also valid for extended objects or also for point objects. Now, of course, for example, if you take, let's say, such an object, put it over here, well, there's some force acting at this point, there's some force acting on this point. So if you want to use the Newton's third law, well, the forces acting on this desk, the total force acting by my case is somewhere in that direction. So the total force that the desk exerts on my case is in this direction. Newton's law is still valid. Or you can look at the different components. You can say that, okay, my desk is exerting a force in this direction over here and in this direction over here. So there is a reaction force at this point acting in this direction and the reaction force acting at this point in this direction. Again, the sum is nevertheless in this direction. You know, for extended objects, you have kind of this freedom that you can, even for a given force, you can just write it as the sum of different forces. So just like in this example, you can talk about the force that this case exerts on the table, which will be somewhere in that direction, or you can talk about the force that the top exerts, which will be in this direction, and this other lid exerts, which will be in this direction. But in any case, all three Newton's laws are valid in any case, in every case. Questions? Okay, let's give a break and we will continue after the break.